Save it 1 second. Okay. Elements and compounds. As I just said, this is a bit of a longer chapter. We're going to be talking about all sorts of stuff, but keep in mind, it is a lot of content. It feels more like 2 chapters than 1 chapter, so don't get freaked out if it feels like a lot. We've talked a little bit about atoms. We've talked about matter. All matter, everything that has mass and takes up space, is composed of atoms, all of it. Every single little bit of matter is composed of atoms. Atoms are the smallest little piece of our elements on our periodic table. So an atom is the smallest identifiable unit of an element. So anything that's on our periodic table, all 118 entries, all of those, when you break them down to the smallest piece, is 1 atom. You can think of it like a nickel or a penny or a, it's the smallest amount of a thing. Our elements are substances that can't be broken down into simpler substances, which is a lie, but it's mostly true. So anything that's on the periodic table of elements, all 118 options, you can't break them down any simpler than an atom. These are all listed on the periodic table. Some periodic tables don't have that written in, so like the one in class for 113, 115, 117, 118, they're UU and then something else. Un, and then something else, like octium, un and octium for 118. Those are all named now, it's just that our periodic table is a little bit old. They were named in 2019. But they exist, or they have existed at least. Atoms are really, really small. We talked about how small atoms are. With respect to human hair, you'd have to have I think it was 10 million atoms to stretch across, touching, to stretch across the human hair. So they're unbelievably small. And we've got another example here. So if you take atoms and line them up with your little finger, assuming that your little finger is about 1 centimeter, it would take about 18 million atoms to cross that distance. And I think most of us probably would have trouble imagining even 100,000 or 1 million. So fill up the biggest football stadium, either type of football, and then times it by 10, times it by 10 again. I think 100,000 is about the max capacity for a stadium, right? So 20 times the largest stadium in the world's worth of people, but atoms end up across your finger and you're barely stretching that distance. So they're very, very small. The idea of atoms has actually been around for a really long time. It's been around since 5th century BCE or BC, depending on which version you like. We use BCE in here because that's what people are using now. So people have suggested these ideas for a long time. They just didn't have any proof because they didn't have any fancy scientific instruments. So Democritus, the one that suggested this, he said, if you divide matter into smaller and smaller pieces, you should end up with tiny indestructible particles, which makes sense, right? Everything that we know, like a table, a person, a chair, a piece of paper, you could cut it in half, you could cut it in half, you could cut those tabs in half, you could cut those tabs in half, right? You keep cutting it into smaller and smaller pieces, and it seems reasonable that eventually you would get to something that's the smallest amount that you can have of the thing. So that's basically the idea here. You can't cut it in half anymore once you get down to atoms. So the name atomos means indivisible. It's their smallest unit. These ideas weren't widely accepted until around 1800, which was more than 2,000 years later. So CE instead of BCE. So Common Era or AD, depending on which version you like. So a long time later. And they showed up in John Dalton's atomic theory. In John Dalton's theory, each element, things on a periodic table, are made up of atoms. That's the smallest building block, the smallest unit. If you have atoms of a given element, under John Dalton's atomic theory, they have the same mass and other properties that distinguish them from the atoms of other elements. This would be basically like if we think about, instead of a periodic table of elements, if we had like money from every different country in the world, you take like coin money from every country, all of the nickels should have the same mass, same properties, are worth 5 cents as the nickels from the rest of the United States. Reasonable. All euro coins should be the same size, they should have the same properties, they should be worth the same amount of money as all the rest of the euros. So it's this idea, but for elements, and it's mostly true. We'll talk about when it's not true later, much later in the class. Another point here is that atoms combine in simple whole number ratios, whole numbers being 1, 2, 3, and so on. Simple whole number ratios to form compounds. So you're not going to have half of an atom of hydrogen bonding with atoms of oxygen, for example. It's always going to be single number amounts. So we're not going to have any fractions in our ratios. And that follows from the first point. They're indestructible particles. You can't have less than one thing, less than one atom. In 2013, so within our lifetimes, I'm not looking forward to the day when that's not necessarily true for everyone in the class, but I think we were all alive in 2013. Scientists at IBM Research used a special microscope. It's called a scanning tunneling microscope. That's not particularly important, but we'll talk about it a couple more times. They used an STM, a scanning tunneling microscope, to move carbon monoxide molecules. And then they took pictures of them. So they have this tiny little surface, and they, at very cold temperatures, just kind of use this to push these carbon monoxide molecules around, and they made these pictures. So this is from a short film, a stop motion film. The film size is 45 nanometers by 25 nanometers. Nanos are prefix for 10 to the minus 3. So if you think of meters, which is about 3 feet, to millimeters, which are really tiny, do that size change 3 times, from meters to millimeters to micrometers to nanometers. And that's sort of the film size that we're talking about here. So you wouldn't be able to see it. Like, you could put this stop motion film on a piece of dust. So they did that. That's the world record for the smallest stop motion video, I think. Something like that. You can watch it online. It's free. I think it's called an atom and a boy and his atom or something. I don't remember exactly. Okay, so we talked about atoms being indivisible and how that's not really true. Atoms are actually made of other things. So atoms are made of some things that you might have heard of. Protons, neutrons, and electrons. These are the 3 components to atoms. All atoms have at least 2 of these. Most of them have all 3. Protons and neutrons, these are the big boys. So protons and neutrons are where basically all the mass is. So all the mass is from protons and neutrons. And then electrons have almost negligible mass. They do have mass, so they take up space, they have mass, they're matter, but they're so small that we just ignore them. They're like a rounding error in terms of thinking about our mass. This would be like if you're weighing yourself in the morning and you've got like a ring on. Like, you're not going to necessarily take all of your jewelry or earrings out every single time you weigh yourself. You'll just like, it doesn't really weigh anything. It's not going to change the difference of what I get on the scale. You can just leave it on. That's sort of our electrons here. And then one of the units that we use to measure these is the aptly named atomic mass unit. It's a very small unit of measure. It's defined as 1/12 of the mass of a carbon atom with 6 protons and 6 neutrons. that's not all necessarily that important, but basically our takeaway from this, so if you have 6 protons and 6 neutrons, 1/12 of 6 plus 6 is 1, so it's about the average mass of a proton or a neutron. So protons and neutrons have a mass of about 1 AMU. And some of the mass numbers are on our periodic table we can think of as in AMUs. So if we look at carbon, for example, up here in the class, carbon, C underneath it, 12.0108 below, that we can think of as atomic mass units. There's some other units that we'll use later, typically when we're looking at those, but atomic mass units, the number of protons and neutrons. So looking at each of our individual particles, these are our subatomic particles, they make up atoms. They've got some symbols that aren't super important right now. They've got masses in AMU, protons and neutrons each having 1, electrons having a very small number. And they've got some other information, charge and all that, and we'll look at those. Okay, so a comparison. To give us an idea, to try to give us an idea of the difference, I didn't cover up enough stuff. To try to give us an idea of the difference in the size, the proton is about 2,000 times more massive than an electron. So if an electron is just like a normal sized watermelon, watermelons are pretty heavy, they're about 20 pounds on average. So if our electron is a 20-pound watermelon, our proton or our neutron is a semi-truck. So if you can imagine getting hit by, or something getting hit by a watermelon, not fun, versus getting hit by a semi-truck, 2,000 times less fun. One of those is extremely much more bigger than the other one. Semi-trucks can go up to like 80,000 pounds, but we're not worried about those big ones. All right, so we need to know about each of the subatomic particles. We need to know how to find the number of subatomic particles. And so we're going to talk about some of those things. So the first up, the big one, the number of protons. The number of protons in the nucleus. The nucleus is where protons and neutrons live. The number of protons that an element has, or that an atom has, defines the element. So if you change the number of protons, you change the element. Changing the number of protons changes the element. This is what the identity of the element is based off of. And the quantity, the number of protons, is called the atomic number. The atomic number shows up on our periodic table as well. So going back to carbon, just because we looked at that one before, the 6 in the top right corner, it's often usually at the top of the box, that 6 means that it has 6 protons. If we find sulfur, S is 16, or sorry, Z is 16. Z is the symbol for atomic number. And you can find these other ones. So any element that you're given, you look in the top of the box that it's in, sometimes the top right corner, that's the atomic number, the number of protons. Z is short for, does anyone know it? Just the letter Z. Why do we use Z? I didn't expect anyone to know it. It's short for Zoll. That's why I didn't expect anyone to know it, which I'm told, thank you, Internet, is German for number. Because Germans were big in the chemistry scene for a long time. I think they still are. So it's Z because of Zoll, which is German for number, atomic number. This is just the number, the ordering that they put them in before they had the periodic table. So that's why it has that symbol Z. There's another way to remember it that I think we might look at soon. All right, so our periodic table, if it's fully listed, fully labeled, is going to look something like this. You can see we've got OG down here versus the UUO that we've got in the classroom. So this 1 means 1 proton for hydrogen. AKA Z equals 1. It's the first one on the periodic table. We've got other subatomic particles, though. It's not all about the proton, even though the proton is very important. We also have, to go along with our Z, we have an A. The A is mass number. And this is the total number of protons and neutrons. Basically, the number of massive particles. Since the electrons are really small, the number of massive particles in the nucleus. And again, the nucleus is where the protons and the neutrons live. If you've watched Big Bang Theory or Jimmy Neutron, those shows I think both have representations of atoms in them, where there's like the dots in the middle, and then, let's see if we can do this. There's like these orbit tracks around it, something like that. This bit in the middle, that's the nucleus. So you've probably seen the shape before. This is just one way that we would represent it. It's all the bits in the middle. The protons and the neutrons kind of stick together, they clump together, and then the electrons are the ones that are around the outside. And A is short for, does anyone know it? It's also German, so I don't expect you to know it, or at least I think it is. I believe it's Atomgewicht. Which translates to atomic mass, or atomic weight. So thank you, Germans, for making our American lives a little bit more inconvenient. It'd be great if we spoke German, but we don't, so here we are. So that's where the A and the Z come from. Z for Zoll for number, A for atomic weight. And the two things that contribute to atomic weight are the protons and the neutrons. So if you add up the number of protons and the number of neutrons, you get your mass number A. So it's a little bit more tricky, but we can find the number of neutrons. The number of neutrons is the difference there we go, difference between A and Z. Since A is our protons plus neutrons, so if we subtract Z, which is the number of protons, we're left with number of neutrons. So you might want to memorize these formulas. You don't have to, but you might want to. If you can't just like poof them into existence from your brain, which I guess would be sort of the same as memorizing them, wouldn't it? Okay, so that's our protons and our neutrons. Let's talk about some other things that show up on our periodic table. Our periodic table is going to have all of our elements, all 118 of them, and we represent them with their unique chemical symbol. that are a 1 or 2 letter abbreviation. With these 1 or 2 letter abbreviations, the first letter is always capitalized, the second letter is always not capitalized. If there's a second letter. So the second letter is lowercase. And just like with calories and calories, this is an important distinction. We have to have them capital or lowercase. If you write it out incorrectly, it becomes a different thing. So for example, we might have something that has carbon and nitrogen in it. Capital C, capital N, those are the symbols for carbon and nitrogen. They're right next to each other on the periodic table. If you write capital C, lowercase n, that is a different element. That is copernicium, which we're unlikely to encounter. There are, I'm sure, a bunch of other examples of when capitals and lowercase make a difference. Some of the names for the chemical symbols, or some of the names for the elements make sense. They match up with their symbol. This is a list, a table of some that don't necessarily make sense because they've got historical names. They're often based in the Latin or the Greek. So potassium, which seems like it should start with a P, is instead K for kalium. Sodium, in our part of the world at least, is called sodium instead of natrium. Other parts of the world actually call it something like natrium. It's got symbol Na. Two that I like for remembering for in here, that I've got little tricks for, is lead. So lead comes from the name plumbum, which is not that exciting. But PB, what else? What's PB? PB is peanut butter. Peanut butter is, I think, at least it's kind of thick, viscous. It's kind of hard to work through. Lead is a relatively soft metal. Like if you got like a rod of lead, you could probably just bend it. So I think peanut butter and lead, those go together in my brain. You shouldn't mix the two and eat it, though, because lead's bad for you. And then the other one is tin. And there's a tool associated with tin. It's got tin in the name. Does anyone know what it is? Tin snips, or shears. They're like scissors, but for cutting through metal. So that's that snips part, the SN part of snips, makes me think of tin. You could probably come up with your own things as well, but those are just some suggestions. Do we have any questions so far about our Z, our atomic number, our A, our atomic weight, or atomic mass, symbols, or names? Cool. Find for me the name and atomic number for each of these elements. We'll practice drill. All right, Na, who's found Na? Na is sodium. And what is its atomic number? It is 11. So if we look at the class periodic table, it's way over on the left side. It's in the third row, the first column, Na, and it's got that 11 in the top right corner. That's our atomic number. What about Ni? Ni is one that makes sense, nickel. And what number is nickel? It is 28. Nickel shows up sort of in the middle of the periodic table. It's in this long cutout section. It's the first row of that. The 28 in the top right corner. How about P? P is another one that makes sense. Feels like it should be potassium maybe, but potassium, remember, is K. So P is phosphorus. Phosphorus shows up in the right side of the periodic table, and it's number 15. So it's atomic number 15. And then Ta, what is Ta? Ta is tantalum. Tantalum shows up sort of in the bottom left corner of the periodic table, and it is number 73. It's in group 5. Tantalum number 73. Questions about how we got any of those? Perfect. All right, so I sort of alluded to the order of things on the periodic table. The periodic table that we have now is not the way that it was always ordered. So we have Dmitri Mendeleev to thank, or Mendeleev, I'm not sure how it's pronounced, to thank for the periodic law and the current layout of the periodic table. He brought some sense and order to the periodic table. So it may have previously been laid out in this long row, like they would have just had a big rectangle, and that's all the periodic table elements, which is, roughly what we've got, but there's actually a little bit more order to the way that we've got it laid out now. We've got a little skip in here. So the way that we have it laid out is that it's arranged in order of increasing relative mass, and certain sets of properties occur on a regular basis, on a repeating basis, so periodically, or on a period, on a set like time scale, it repeats. So Dmitri Mendeleev noticed this, and he started laying out the periodic table with all the elements that they knew at the time, started laying it out in a way that he could get extra information from the periodic table. We don't know any of that information now, but as we start to learn it, it will become increasingly helpful to us. So that's why it's called the periodic table of the elements, is because it's got repeating patterns. So for now, the takeaway from this slide is we're just going to accept that it's the way that it is. We'll learn more about why things are the way they are in a couple of chapters. We'll learn some of those cool tips and tricks. Some things that we can learn now, though, are there are a couple of ways that we can categorize things on the periodic table. So metals, nonmetals, and then things that are sort of in between, which are semimetals or metalloids. Metals are things that we would think of as metals, things like iron, nickel, cobalt, chromium, copper, gold, silver, platinum, iridium, stuff like that. Metals generally occur in the lower left-hand side of the periodic table. Left slash, not tower, lower. Left side of the table. And then we've got nonmetals. Nonmetals are kind of in the upper right corner of the periodic table, just generally. Hydrogen is also often put in with the nonmetals. Other periodic tables just kind of like throw hydrogen like up in the middle by itself completely, because hydrogen's a little bit weird. So our nonmetals are the upper right corner. And then the semimetals or the metalloids are in between. And those ones are a little bit fuzzier. Like you can't just like look at where things are and like, all right, well that's probably this, that, or the other thing. Okay, so metals are most of the periodic table, the left side, the lower left side of the periodic table. They all have similar properties. They're good conductors of heat and electricity. Things like copper conducts heat and electricity really well. You can pound them out into flat sheets. You can pull them out into wires. They're often shiny. Those are all properties that we could probably think of if we spent long enough thinking about metals. And a new one, an important one for us, metals tend to lose electrons when they undergo chemical changes. Why am I boxing that in? It's important. I'm boxing it in because it's important. So metals tend to lose electrons when they undergo chemical changes. Nonmetals have other properties that are also sometimes similar. Some of them are solids at room temperatures, others are gases. Generally, they tend to be poor conductors of heat and electricity, and these tend to gain electrons when they undergo chemical changes. So things like oxygen that we need to breathe, nitrogen that's also in the air, chlorine, like we might see in bleach, iodine, like you might use for cleaning your water if you're going backpacking or camping. And you also need a little bit of iodine in your diet. But the big one here for nonmetals, they tend to gain electrons when they undergo chemical changes, and they occupy that upper right side of the periodic table, hydrogen often included, even though it's in the upper left. And then our metalloids, or semimetals. These are that zigzag diagonal line. Sometimes, like I think on our yellow sheet, there's a little staircase thing. So anything that's like along there would be a safe guess to call it a semimetal, unless you know that it's not a semimetal, like aluminum is a metal. This one's a little bit more nebulous about whether it's a metal or non-metal or semimetal, kind of along that zigzag. These also have mixed properties. They're also called semiconductors. So semiconductors, metalloids, have this interesting property about them where you can change different elements about them. Not elements, but you can kind of tune and change the conditions and the way that like you prepare them or way that you set them up and have controlled or changed electrical conductivity. So that's why they're often called semiconductors. And the one here that you should know, the big one, would be silicon. Silicon, if you didn't know, is like in all of our electronic devices. If you've ever like looked at an old computer or an old TV, like they've got those like, usually they're like green chips, green wafers. Those are silicon wafers. So they kind of make up the backbone of a lot of our electronics. All right, if we want to classify things as metals, nonmetals, or metalloids, we can do that, or at least we can make some guesses about it. So let's find Se, selenium, on our periodic table. Bink, there it is, Se, selenium. Based on its location, what do we think selenium might be? A metal, a nonmetal, or a metalloid? Yeah, I would say that it's probably non-metal. You also might have guessed metalloid, because it is pretty close to that line. How about Mg? Bink. There's Mg. It's in the top left. The periodic table, it's number 12. What kind of thing is magnesium? Is it a metal, non-metal, metalloid? It is a metal. It's very firmly way over to the left of the periodic table. It is definitely a metal. You should definitely categorize it as such. How about GE? Find GE. Bink. GE germanium, number 32. What kind of thing do we think GE might be? You might think it's a metal. GE, if I'm remembering correctly, is a metalloid, but you might have guessed that it's a metal. And then what about AG? Let's find AG. Bink, AG. AG is silver. Is silver a metal, non-metal, or metalloid? Yeah, silver is definitely a metal, often used for jewelry and making shiny things. And it's kind of more to the left, that lower left side of the periodic table. It's not in the upper right, it's along that zigzag line, so it's a metal. Questions? All right, other ways that we can break things down. One big category break is we've got main group elements and transition metals or transition elements. Part of the reason that we separate these two is that our main group elements have very predictable properties. So if it's in the main group, we can make some really good guesses about what the properties are going to be like, how it's going to behave, and more often than not, we're going to be correct. And our main group elements are these two sets of outer blocks. So our first two columns and our last 6 columns. And generally, these have very consistent properties throughout. So we'll be able to make some good predictions about how those things behave, even though this is like the very first chemistry class, baby's first chemistry class, if it were a book. And then our transition metals in the middle, these are a little bit funky. So our transition metals have some properties that we might be able to predict, but they're a little bit less consistent and it's a little bit more each metal for itself. So each of those elements is going to behave maybe a little bit differently than we'd expect. So we won't be making any big guesses about transition metals in this class. When I took a class that covered transition metals, I think the first class that it really showed up in inorganic chemistry, which most of you are not likely to take unless you're doing a chemistry major. So that would be 3rd or 4th year chemistry. And then we really dug into it in my graduate level class that was focused on transition metals and transition metal chemistry. So this is like that kind of level of complexity within transition metals. It's kind of weird stuff in there. You'll talk about it a little bit if you take Chem 1B though. And then we've also got our lanthanides and actinides, which we kind of just ignore. They're there, but we're not going to really talk about them that much. So big separation. Main group, that's the outside bits, and then the transition metals, that little rectangle in the middle. Transition metals are weird. Those different, the reason that we call it main group is another name for like a column, group, or family. So column equals group equals family, the single strongest force in the universe, if you're in Fast and Furious at least. So our groups, our families, our columns. The periodic table class that we have, if you look in the top left corner, it says group. So that's a nice reminder that these are groups, 1, 2, all the way numbering up to 18. There's 2 different numbering systems. There's 1 to 18. There's also an A-B version that we'll see, I think, later. Some of these groups have names, special names, and we'll talk about some of those special names. So our first special name, this is one that you should know. is alkali metals. So our alkali metals are the first column. The very first group on our periodic table. These are very reactive metals. The reactivity increases as you go down up until the point that you get to cesium. Cesium is the most reactive metal on the periodic table. Lithium, if you buy like lithium from a chemical supplier, usually it's shipped in oil. The oil prevents it from reacting with just air. If you just leave lithium out, it starts to react with the air, and it sort of goes bad. You'd have to sand it down every time you wanted to use it. So that's why it's usually stored in oil. Once you get to like sodium and potassium, if you put sodium and potassium in water, they'll actually like light on fire and like dance around the surface of the water. You can look up videos of all these. And I think rubidium explodes, and cesium definitely explodes. So if you get a little chunk of cesium, like pure cesium, you put it in like a little like gel capsule, like you might take your medicine in, and you like throw it in some water. As soon as that gel capsule dissolves in the water, boom, explosion. That's how reactive it is. And francium doesn't exist in like significant amounts. I think there's like 3 grams in the world right now. In that ballpark. Small amounts of francium. So that's our alkali earth, or alkali metal, sorry. And then we've got next to it the alkaline earth metal. The way that I remember alkali and alkaline earth is alkali is 1, 2 is bigger than 1, alkaline earth is longer than alkali. It's just the bigger name. So alkali, then its big brother alkaline earth metals. These are fairly moderately reactive, not as explosively reactive as our alkali metals. Much tamer. So everything that's in that second group, that second column, those are all going to be our alkaline earth metals. Some of these things you might see like possibly in fireworks. Alkali earth metals as well. Okay, so you should know both of those groups, like where they're found. If I give you a metal, you should be able to tell me what group it is in. You might be able to give me the name as well. Skipping all the way to our second to last column, things that start with fluorine, so group 17. The name for this group is halogens. And our halogens are very reactive nonmetals. Nonmetals because they're on the right side of the periodic table. Our metals are on the left side of the periodic table. Things like fluorine, chlorine, bromine, iodine, astatine. And now is when I'm choosing to point out the A versus other categorization. So the A for group 7A, A just means its main group. So if we skip our transition metals, then our alkali metals are group 1 or 1A. Our alkaline earth metals are 2 or 2A, skipping all the way to boron, B, 13 or 3A, 4A, 5A, 6A, 7A, 8A. So our A designation goes up to 8. There are some instances where we'll use that A designation because it's handy. A lot of the time, though, we might just say that it's group 17 instead of 7A. So that's our third named group. And our fourth and final, oh wait, actually before I talk about that, I want to be pedantic for a little bit. Something that somebody pointed out to me, fluorine, chlorine, bromine, the end we're saying ene. How would you pronounce this fourth one? A lot of people say iodine. That doesn't fit with the way that we pronounce the other ones, so I say iodine. You don't have to say it that way, just somebody when I was taking my chemistry class in undergrad pointed that out, and I was like, you know, that's a fair point. And so I've been pronouncing it iodine since then. But up to you, whatever you want to do. Okay, our last group our last named group at least, are the noble gases. The noble gases are chemically inert. They do not react. Which is mostly true. They're not going to react under normal conditions. It takes an act of science to get them to react. And these are going to be our group 8A or 18. So this is our fourth and the last one that you need to know with a name. So helium, neon, argon, krypton, xenon. So a big part of the reason that we use helium in like party balloons is because it's lighter than air, so that it's less dense in the air around it, but floats. And because it's chemically inert, it doesn't explode if you accidentally light it on fire. Hydrogen gas, hydrogen is also lighter than air, but it's not chemically inert. And so if you fill up party balloons with hydrogen and you accidentally pop one or you get one too close to your birthday cake, it explodes. Like very loud, deafening explosion, possibly very dangerous. So don't try it at home even if you have the hydrogen around. So that's part of the reason we don't use hydrogen in party balloons, because we don't want fireballs around our birthday cakes, because that's what would end up happening. This is also the reason why you can do that fun party trick where you like suck some of the helium out of a party balloon. And then you start talking and your voice gets pitch shifted up. It gets pitch shifted up because the lighter or the less dense helium travels faster with your vocal cords, and so it vibrates in a different way. And you can do that safely as long as you don't breathe in too much, because you'll pass out from not getting enough oxygen. Other than that, though, you can do that trick and it's really safe. Neon we use in neon signs, partly because it's chemically inert, so if you accidentally break the neon sign, it doesn't explode. You just, broken glass to clean up. Another fun party trick that you can do, but it's a little bit harder than the helium one, is argon gas is also chemically inert, so it's relatively safe for you to breathe it. If you get argon gas, argon is denser than air, so if you breathe it in and then you start talking, it actually pitch shifts your voice down instead of up. So helium pitch shifts you up, argon takes your voice down. You can look up videos of people doing that. I'm sure that there's tons of them on YouTube. So those are your fun facts. The big takeaway: noble gases don't react. They're called noble gases and they're group 8A. All right, find which group or family of elements each of these elements belongs to. If it's named, use the name of the group as well. All right, let's find first these elements, and then we can decide what group or family they belong to. So lithium, Li, we find in the top left of our periodic table. It's number 3. What is the number of that group or column or family? What number is it? 1. It's number 1. We might also call that 1A. And what is the name of that group? Yeah, it's the alkali. Alkali what? Metals. Alkali metals. We've got Ar, which is short for argon. All the way on the right side of the periodic table, it's number 18. What group number is that in? It's 18. With our A designation, it would be 8A. And what do we call that group? Yeah, those are our noble gases. And we also have Cl. Cl is right next to Ar. It's number 17. Cl is short for chlorine. What number is that group for Cl? What number? Yeah, it's 7 or 17. So 7A/17, as somebody pointed out, those are halogens. And then we've got, last but not least, SR. And SR for strontium is in what numbered group? Two. Number 2A/2. And what do we call that group? Alkyl what? Alkaline earth metals. Thank you. So those are alkaline earth metals. Questions about groups or families? All right, so previously we talked about stuff with protons. If you change the number of protons, you're changing elements. So for example, carbon has that 6 in the top right corner. That's 6 meaning that it has 6 protons. If you change it, if you give it another proton, then it would turn into nitrogen, would have 7 protons. So changing the number of protons changes the element. We can also change the number of electrons that we have. This often happens in chemical reactions. And we call these charged particles ions. So normally, like typically if you just find one of these elements out in the wild, normally an atom is neutrally charged, meaning it has no excess positive charge, it has no excess negative charge. The protons in an atom are positively charged, so that number in that top right corner. Protons are positive and positively charged. Electrons are negatively charged. That was in that little table. I just forgot to talk about it. And they have the same size of charge. So our protons have a +1 charge, or 1+ charge, and our electrons have a 1 negative or a -1 charge. So for carbon, if it's going to be neutrally charged, if it's going to have a charge of 0 and it's got 6 protons, how many electrons does it need to have? So carbon has 6 protons. How many electrons does it have? Yeah, it's also 6. So for all of our elements on the periodic table, if they're neutral, if they're not an ion, if they're not a charged particle, then that atomic number, whatever it is, 1 through 118, is also the number of electrons that we would expect it to have. So ions are when we've lost or gained electrons. And sometimes talking about things in terms of like losing or gaining electrons will be a little confusing because electrons are negatively charged. So just keep in mind it can be a little confusing. We've got 2 special names for atoms or for ions. One of those names is cations. So positive ions are called cations. And negative ions are called anions. I've seen some people write that positive cats, positive cations, paws in cats. You know, cats have paws. The things they use to make their biscuits. So that could be one way that you'd remember them. Positive and cations, negative and anions. Put a little bracket so you know that they're important. When we write out ions, things that have a charge, we write the charge in the upper right corner of the symbol. Ion charges are written with the number first, followed by the charge. So I would read this out as barium 2+. So this is barium with a 2 positive charge, or phosphorus 3-, or phosphorus with a 3 negative charge. The order is important to me. It's also important, I think, to other people, but it feels like it's especially important to me for reasons I can't explain. So get it right. I'm smiling. Just for people on the video, because I don't do video. All right, so ions that lose electrons. Let's look at examples of that. In reactions, lithium atoms lose 1 electron, 1 E-, and they form lithium plus ions. The 1 is omitted or left out. So if there's not a number, assume that it's 1. This is a common theme. Chemists love to save time writing and in other ways. So we'll often leave off 1s where we can, and we'll often leave off letters for abbreviating things when we can as well. So this is lithium 1+. You don't have to write the 1. The reason that it's 1+ is because it lost a negative charge. So it's got 1 fewer electron. It normally has lost a negative is like -1, so it's +1. This is where this can get confusing. So our ion charge, you can use this formula for anything. Ion charge is equal to the number of protons minus the number of electrons. The order is important here, otherwise you'll get the wrong sign. Some of you may be able to just think about, okay, I've got this many positives, this many negatives, and like immediately your brain puts it together and you get the charge. Awesome. You don't have to use this formula. This formula is for the rest of us. So for a lithium plus ion, that's going to have 3 protons and 2 electrons. So we do 3 protons minus 2 electrons, 3 because it's a positive, 3 for the protons, the -2 because it's a -2 for the electrons. We get an overall 1+ charge. If I told you that lithium changes by 1 electron when it reacts, there's a way that you can remember whether it gains or loses. Who remembers why it loses? Something related to why it loses an electron. What kind of element is lithium? Where is it on our periodic table? So on the left, it's a metal. Metals tend to what? Lose electrons when they go through reactions. So metals are going to tend to lose electrons, meaning that metals tend to form positive ions. Metals usually form positive ions. What do we call a positive ion? It's one of those 2 special names. Cations. So metals usually form cations, positively charged ions. You can also gain electrons. So in reactions, fluorine will gain 1 electron, So we've got a little reaction diagram here. We've got fluorine, neutral fluorine, plus 1 electron. It's got a 1 negative charge. We leave the 1 off. Together they form F minus, fluorine with a 1 negative charge. Again, this is the same equation from earlier. Ion charges, protons minus electrons. So F minus has 9 protons and 10 electrons. So put the 9 in, put the 10 in. We get a minus 1. We flip the numbers because we like to keep things interesting in chemistry. So our overall ion charge is 1 negative. Another way that we would know this is that fluorine, being a halogen, is a nonmetal. It's up in this upper right-hand corner, this upper right quadrant of our periodic table. So fluorine, being a nonmetal, nonmetals tend to gain electrons, tend to form negative ions, or negatively charged ions, which we call what? Anions. So nonmetals tend to form anions. You might be thinking to yourself, Mr. K, what about our third group, metalloids? What about semimetals? What do they do? We're not going to talk about it. They don't really. You're welcome. Okay, so that's gaining electrons. So we've talked about changing 2 of our subatomic particles. What's the first particle that we talked about changing? Who remembers? What's one of the 2 that we talked about changing? You've got a 66% chance if you're guessing blind. What was one of the 2 subatomic particles, the little ones that make up the elements? Protons. What happens if you change the number of protons? What's the new thing? What does it change into? It changes into a new element. And then here we're talking about changing electrons. When you change electrons, you're changing ions. So it's becoming an ion. So if you change the number of electrons, it turns into an ion. If you change the number of protons, it turns into just a different element. And within ions, we have cations positively charged, anions negatively charged. We can also change the number of neutrons, our third subatomic particles. And these are isotopes. So all atoms of a given element have the same number of protons. Those 2 things are linked. The identity of the element and the number of protons are intrinsically linked. You can't separate those 2 from each other. However, the number of neutrons can vary. You can change the number of these neutrally charged particles . So neutrons have our neutral charge, no charge, 0 charge. You can change the number of neutrons that show up in an atom. And this, I mentioned earlier, contradicts Dalton's theory. So Dalton's theory was that all atoms of the same element have the same mass. It's not actually true. An example of this with a money version, if I'm remembering correctly, Mexican pesos. There's old Mexican pesos and there's new Mexican pesos. The old ones are worth like 1,000th of what new Mexican pesos are. So even though it's still a peso, right? It's not the same peso. It's got a different value. So that's sort of what we're doing here, right? We can change the value of the neutrons. They're not going to have the same mass. It's still the same element, though. The way that we distinguish them is we call them isotopes. The iso prefix, I believe, means same. Not 100% sure on that. I'll have to look into that. Let me just, we'll delete that. Anyway, isotopes have the same number of protons, so they're the same element, but they have a different number of neutrons. So a different mass. And all elements are going to have their own special natural abundance of isotopes. And these factor into the mass on the periodic table. So the reason why for carbon often has 12 protons and 12 neutrons, sorry, 6 of each, a total of 12. The reason that it's 12.0108 is there's also a little bit of carbon-13 and a little bit of carbon-14. So on average, it's usually going to be 12.0108. Sometimes you might be a little higher than that. Sometimes you might be a little bit lower than that, just because there's like a range of different carbon values. For something like chlorine has two main isotopes. I think it's 35 and 37. And those have different natural abundances as well. There's a lot more 37 relative to the ratios with carbon. So that brings that number up from the 35. 35 is the most common. There's also a lot of 37. So we average those two together and we get 35.45-ish. That's where those numbers come from. You don't need to memorize any of the abundances. Questions so far? Okay, we will take a break here and then come back in about 10 minutes. All right, jumping back in. We talked about changing different numbers of different particles. I mentioned earlier a little bit about natural abundance. So the majority, all of the elements on our periodic table have different isotopes. And they've got their own distributions, their own numbering of them. We're looking at hydrogen as an example here. There are specific names for hydrogen of the three isotopes. You don't need to know them, but they're protium, deuterium, and tritium. Protium has one proton, no neutrons. That's normal hydrogen. Normal hydrogen, just a proton. There are also forms that have one neutron and forms that have two neutrons. Those are different isotopes. These are relatively rare compared to normal hydrogen, and that's why our atomic mass for hydrogen, if you look at your periodic table, is about 1.08. There's not very much of the deuterium or the tritium just out and about in nature. Those weird symbols are called isotope symbols. Isotope symbols often look like this. This is the way that we'll see them in the class. There's some other ways that we can do them, but these are kind of the more important ones. So there's three main parts to an isotope symbol. The big part, the letter part, is the element symbol. So whatever the periodic table says is its element, one or two letters, that goes here. And then there's two numbers. The two numbers are mass number. Does anyone remember what the symbol for mass number is? What's the letter? It's A. Mass number has a symbol A from that German atomic Gewichte or whatever, atomic weight. And then we have also got our atomic number, which is what? Z. So we've got our A to Z. So our mass number on top, our atomic number on the bottom. So another way that we could symbolize this is A over Z and then X standing in for our atomic symbol. A convenient thing about this is that with the exception of protium, normal hydrogen, A being our mass number, the mass number is the number of protons plus the number of neutrons. Our atomic number is just the number of protons, so if it has any neutrons, our mass number is going to be bigger than our atomic number. So we'll have big number over little number, or A over Z. So a couple of nice ways to remember where the numbers go. So bigger number goes on top, and the little number goes on the bottom. Or the atomic weight goes on the top, and The atomic number goes on the bottom. The common isotopes of neon are 20 over 10 neon, 21 over 10 neon, 22 over 10 neon. Another note that I'll point out for us about these is that the atomic number and the symbol are linked. Every time that we've got neon, it's always going to have atomic number 10 because that's the number of protons. The number of protons defines the element. So 10 will always go with neon, the same as, like with carbon, 6 will always go with carbon. So these would be some isotopes of carbon. It's always 6 with the C. For isotopes, the one that changes is that mass number, that A value. Questions about our isotope symbols? As a reminder from earlier in the lecture, mass number A is the sum of protons. Protons are positively charged, and neutrons. Neutrons are negatively charged. Sorry, neutrally charged. Brain? Neuter for neutral. Pro, I'm in favor of. Positive. Electrons don't have a fun one for that. They used to be called negatrons, nega like negative, and they changed them for some reason. I think negatrons is fun, but we call them electrons now instead. So this is just all review stuff. There's also another notation that we can use for isotopes. This is more typically how you'd see it written out in text, because you don't have to do the superscript subscript. So Ni59 or nickel 59. So you either use the element symbol or the element name. So for those carbon isotopes that we saw earlier, C12 or C14, two of the isotopes of carbon, or we can write it out, carbon 12 and carbon 14. And there's a slight typo here, nickel should not be capitalized. So this is an opportunity that I'll take to be pedantic again. Element names are not product names. So what that means is that anytime you're writing out an element name, unless it's starting a sentence, don't capitalize the first letter. If you're using the symbols, like Ni for nickel, you do capitalize it. If you're writing out the full name, don't capitalize it. This is a very technical, minor detail, and you're welcome to just forget it, because it's not really that important. But I'm pedantic, so I like to talk about it. All right, a little bit of practice with isotope symbols. Find the atomic number, mass number, and symbols, all three of them, for the bromine isotope with 46 neutrons. Alrighty, where should we start with this problem? What's some information that we've been given? "46 neutrons. That's important. What else do we know? There's one other important piece of information. Something that we were given, a starting point, something to work with. The element, yeah, we were given that it's bromine. Okay, so we know it's bromine, and we know it's got 46 neutrons. And we are finding atomic number, mass number, and symbols. There's 3 of them. Just so we get practice with all of our forms. What is the symbol just for bromine by itself? Br. Boom. Bromine, Br. We found it on the periodic table. I didn't mean to say it, but I did. Oops. Right, so bromine. We find it on the periodic table. There's some other important information we can get from the periodic table, which is what? We can get the atomic number, which is 35. For bromine, the atomic number is always 35. Since the atomic number is the number of protons defines the element, in this case, bromine. So we've got the atomic number. Where do we put the atomic number with our symbol? We're doing the one with the 2 numbers. We've got a top number, bottom number. Yeah, we're going to put 35 in for the bottom number. 35 is our atomic number. Atomic number goes down below. Atomic number being Z. And then how do we get the mass number? The mass number is the number of particles in the nucleus, that center bit, the number of big particles, protons and neutrons. Protons and neutrons are our big ones. So we're going to do protons plus neutrons. We've got 35 protons. We've got 46 neutrons. So we have 81 for our mass number. And our mass number is this top number. So this is our first form of an atomic symbol or an isotope symbol for bromine with 46 neutrons. What is another form? How else could we put it? We just looked at these. How else could we write out the isotope? Does anybody remember? I remember. All right. Br dash what? 35 or 81 or 46? What number do we put there? Yeah, it's 81. And then that's not even our final form, because we also have, writing it out, bromine dash or hyphen or N dash or M dash 81. I don't remember which one it is. Bromine line 81. That's the important part. So these are all 3 forms. Those are all 3 forms for the symbols for bromine isotope with 46 neutrons. You can convert between any of these 3. The Br81 and the bromine 81, that's the easiest because you're just pairing the symbol with the name. But we could also move from this Br81 to 81 over 35 Br. We would just have to look up the 35 from the periodic table and get the order right, of course. But we can convert between the 3 of those. Questions about those? Confusions? Illusions? Illusions. Okay, great. Working the other direction, how many protons and neutrons are in the potassium isotope given here? Okay, after a little free time to work on it, we want the number of protons and neutrons in the potassium isotope given. So all of our information that we need is given to us here. So 40 over 19K, there's a couple of ways that we can get the number of protons. One way, if we don't remember what either of those numbers mean, we could go back to our periodic table. Take a peek at our periodic table, find potassium. It's one of our alkali metals. It's got that 19 in the top right corner. That 19 is the number of protons. So 19 protons. We can also get that because the same number shows up in that bottom left. That's our Z, our atomic number. So Z equals 19. That's our atomic number. So two places that we can get it from, it's the same number. Then we want to find the number of neutrons. Finding the number of neutrons is a little bit more difficult. What is this 40? What does it represent? Or what would the symbol be that goes in there? Mass. It's our mass number. It's our A. A equals 40. That's what that 40 is. Our mass number is protons plus neutrons. Protons plus neutrons. We know how many protons we have. All right, so let's rewrite this. 40, our mass number, is equal to the number of protons that we have, which we know is 19, plus the number of neutrons, which we don't know. We've got an algebra problem. We can solve an algebra problem. Right, we just subtract 19 from both sides, and 21 equals the number of neutrons. So we have 21 neutrons. Any questions? Beautiful. Let's do some practice with ion charge, because we didn't really do any practice with that. So we want to determine the ion charge for each of these elements based on the number of protons and electrons. So a cobalt ion with 25 electrons, cobalt symbol is CO. So to start, right, we want the symbol, at least for the periodic table that we have in class. So cobalt, CO. We find cobalt on our periodic table. It shows up in our transition metal block. It's in group 9. It's got a 27 in the top right corner. That lets us know we've got 27 protons. So Z equals 27. So the cobalt has 27 protons. Protons are positively charged, so 1 plus charge. So one way that we could solve this, protons are positively charged, electrons are negatively charged. The difference between them, we've got 2 extra protons. So our magnitude is 2. It's protons, so it's a positive charge, 2 plus. Two plus because we have 2 extra protons. The other way that we could solve it is with that equation from earlier. And in that equation, charge equals protons minus electrons. So we can plug in the 27 protons and 25 electrons. And we also get 2 plus, or plus 2. And the symbol that we would write out for this, we weren't asked for it, but just to show us, CO, and then in the upper right-hand corner, 2 plus. There's a way that we can check our work with this. Because what if we forgot the order? What if we did 25 minus 27 and we got 2 minus? How would we know that we were wrong with 2 minus? Any ideas? When we were talking about metals, metals tend to lose electrons when they go through reactions. That means that they tend to form positively charged ions. Metals are generally going to form positive ions. So if we got a 2 minus, that doesn't mean it's impossible, but it's unlikely because it's a metal. Cobalt is a metal. So that might be one way that we would check. I don't necessarily expect you to have that under your belt at this point, but that would be one way that you could check if it was something that you remembered. Wrong, because metals form cations, positively charged ions. Okay, so that would be a check. How about an iodine ion with 54 electrons? Iodine is in our group 17 or 7A, symbol I. It's one of our halogens. I, on the periodic table, has cheeseburger. Sorry, I has 53 protons. And we're told that it's got 54 electrons. So if you know that electrons are negatively charged, protons are positively charged, we've got 1 extra electron, 1 negative charge, because we've got 1 extra negative. So 1 excess negative charge. So 1 minus, I minus. Or we go back to our old reliable protons minus electrons. 53 minus 54 equals -1. Flip the order because this is chemistry and we do it that way for some reason. And we get I minus. So if your brain works with thinking about pairing them up, how many extra positives or negatives, and you can get it immediately like that or really quickly like that, great. Otherwise, you can use this equation. This equation, as long as you get the order correct, won't serve you wrong. Again, a check here would be iodine is in the kind of that upper right side of the table. It's a nonmetal. Nonmetals tend to form anions, negatively charged ions. And then last but not least, a nitrogen ion with 10 electrons. Nitrogen is N. Without moving any further, what kind of thing is nitrogen? Is it a nonmetal or a metal? It's a nonmetal. What are we expecting the charge to be, positive or negative? Negative. Nitrogen is a nonmetal, so we expect a negative charge. Okay, so nitrogen, its atomic number is 7. It has 7 protons. We're told that it has 10 electrons. So we do protons minus electrons. 7 minus 10 equals -3. And our symbol would be N raised to the 3 minus. So nitrogen with a 3- charge. And that fits with what we expect based on where nitrogen is on the periodic table. We can also work the other direction. We can work from the symbol and find the number of protons and electrons. Using sulfur, 2- as an example, the first thing that we're going to start with is we need to figure out how many protons does this sulfur have. So S for sulfur has, look at our periodic table, find S. S is 16. So sulfur has 16 protons. And our equation, our formula, charge equals protons minus electrons. What is our charge? Two minus. We've got a 2- charge. That's what this little 2- up here is. So our charge is 2-. We've determined that we have 16 protons. So equals 16 minus E-. And we're trying to figure out what is E-. We need to do some algebra. I would probably add E- to both sides to move it over. Since we're subtracting E-. Otherwise, we might end up like getting confused with our negatives. So add E- cancels out on the right side. So electrons plus -2 equals 16. Electrons minus 2 equals 16. Add 2 to both sides. Electrons equals 18. So we have 16 protons, 18 electrons. It would also be perfectly fine if you look at, okay, it's a 2- charge. We've got 16 protons. The 2- means we have 2 extra electrons. So 16 plus 2, 18 electrons. If that works for you, you're welcome to do that. Just make sure that you don't confuse yourself. Otherwise, the rest of us, we can do this algebra bit. You could also memorize just the rearranged algebra forms of these. So electrons equals, what did it end up being? Charge plus protons. Something like that. You can rearrange it, or you can come ask me about it in tutorial. All right, we talked about the numbers. The numbers associated with that letter A above each main group column, 1 through 8. The reason that we would use that numbering system is that that gives the number of a special kind of electrons, what we call valence electrons. So valence electrons are outermost electrons. There are different layers of electrons. Another way that we can think of valence electrons is the reaction electrons. If you have a bank account, if you've got a savings account, you probably have a minimum amount of money that you have to have in your savings account or your checking account or whatever. I think it's a savings account usually has a minimum. It might be as low as $1 or $5. It might be a much larger number depending on what sort of contract you have with your bank. The valence electrons is basically like how much money can we actually pull out of savings if we need to. And then there's like some minimum amount of electrons that are always going to be in there. We can't play around with those electrons. We can only play around with the ones on top of that. These are our valence electrons. if we're in 5A, that means we have 5 valence electrons. That's true for anything that is in that 5A or 15. So nitrogen has 5 valence electrons, phosphorus, right below it has 5 valence electrons, arsenic, seaborgium, bismuth, all have 5 valence electrons, for example. Do we have questions about that part? Okay, so that's the number of valence electrons that they have. Our main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. Which is 8. All of our main group elements, so the ones on the outside, not this middle block, all of our outside electron or elements, they want the same number of valence electrons, same number of total electrons as the nearest noble gas, which is 8, because they're 8A. So let's take fluorine as an example. Fluorine has how many valence electrons? 7. Fluorine has 7 valence electrons. What is the nearest noble gas to fluorine? Neon, Ne. So it wants to have, when it reacts, it wants to have the same number of valence electrons as neon. It wants 8 valence electrons. So it wants to gain 1 electron. It gains 1 electron when it forms an ion, meaning that it has what charge? Guesses? If you have no charge and you gain 1 negative charge, what's your charge? That's right, it's 1 negative. So it forms F minus. Okay, moving down to chlorine. Chlorine wants to have the same number of valence electrons as argon, same total number of electrons as argon as well. What charge will chlorine form when it's an ion? What charge will it have? Will it be 0, 1 negative, 2 negative, 1 positive, 2 positive? If fluorine forms a 1 negative, what does chlorine do? It's also a 1 negative. How about bromine? What charge will bromine form when it forms an ion? It wants to be like krypton. Also 1 negative. How about iodine? Also 1 negative. Moving over to oxygen. Oxygen needs to gain 2 electrons to become like neon, so it'll form a 2 negative charge. What charge will sulfur form when it tries to become like argon? If oxygen forms a 2 negative, what does sulfur form? Also a 2 negative. How about selenium, Se? Also a 2 negative. So all of these main groups are going to form the same charges when they form ions, which is very helpful, super helpful for us. The transition metal elements do not do that. Some of them will form +1, a lot of them will form +2 or +3, some of them will form +4. They can form even +5, sometimes +6, occasionally +7, and higher numbers are possible but not likely. And that can be all within the same element. So our main group elements, nice and simple, they form 1 element or 1 ion charge. Our transition metal elements, Nightmare City. We're staying away from those. We will touch on chemical formulas a little bit before we wrap up for today. So chemical formulas are the ways that we represent compounds. They're the shorthand for compounds. So instead of writing on sodium, right, we can write capital N lowercase a. That represents sodium. Our chemical formulas are the same sort of thing. Instead of speaking or saying the whole name, we can condense it into just symbols. It saves us a lot of time writing. Chlorine, the element, we could represent as Cl. Sodium metal and chlorine gas can go together and form sodium chloride, which is not on this slide, even though I thought it was. Anyway, our chemical formulas indicate the elements. We use their symbols that are in a compound and the number of atoms of each. The number of atoms is given by the subscript. The sub is lowered. These small scripts that follow each of these numbers or each of these letters. If we've got a subscript of 1, we leave it off just like we did with ion charge. So CH4, C for carbon, we've got 1 carbon. That subscript of 1 is left off. For hydrogen, H is hydrogen, we've got 4 there, meaning that we've got 4 hydrogens. So if we wanted to like block out what letters and numbers go together, it's always the number that's following. So we've got 4 hydrogens. It only applies for the hydrogens. There's no number behind the C, so we just have 1 carbon. That's our simplest case. We will also have more complicated cases. We can have groups that stick together. So this is where things get a little hairier. We can have groups of atoms that act as a unit. We call these polyatomic ions, assuming they have a charge. The poly meaning many, and then atomic because many atoms. If we've got multiple polyatomic groups, so an example of a polyatomic group would be this PO4 that we see here in our formula. If we've got multiple, then we put parentheses outside, and the subscript follows the parentheses. So color-coded here, the simple part. Up front, we've got Ca for calcium. We've got 3 calcium atoms. I'll block this again the same way I did with the one before. So 3 calciums. We've got parentheses here in orange. Go Tigers. The parentheses mean that we have this whole group. This 2 applies to the whole group. So we've got 2 of these PO4 groups. Within each of those groups, there's 1 P, so 1 phosphorus, and there's 4 oxygens. So if we were counting up the number of everything that we've got here, the simple part is the calcium ions, the calcium atoms that are out front. We've got 3 of them. So over here on the left, 3 calcium atoms. Within each of our PO4 groups, we've got 1 phosphorus. So that's this blue 1. But we've got 2 of those groups. So 2 times 1, we've got a total of 2 phosphorus atoms. For our oxygen atoms, we've got 4 of them in each PO4. We've got 2 of those groups. So 2 multiplied by the 4, we get 8 oxygen atoms. Questions about how we tallied that up? We'll be using notation like this a lot. So if you are confused, please ask questions. Or if you get confused at any point, please ask questions. The specific subscripts in a formula are integral to what that compound is. So some examples here. If we change those subscripts, it's now a different thing. We're referring to a different chemical. This is a little bit like student ID numbers. If you change even one of the numbers, it looks very similar, but it's talking about a different student, right? If you write down your student ID number, it has to be exactly right, or your driver's license number, or whatever, right? It has to be exactly that thing. and then it specifies U. If you change any part of it, it means something else. It's the same thing for our chemical formulas. So CO is the chemical formula for carbon monoxide, which is really bad for you. And CO2, we just changed this from a 1 to a 2. That's carbon dioxide. We're breathing that out. We've all been breathing that out the whole time that we've been in here. It's not that bad for you. You don't want to be in a room that's only CO2, but you can be around it, and it's no big deal. If you're around carbon monoxide, you can eventually get carbon monoxide poisoning and end up like hallucinating or dying. Just by changing that one subscript, right? Those are completely different things. So it's important that we make sure that our subscripts are correct. Any questions before we wrap up? Okay, we'll be picking up right after this next class.